Hi everyone, and welcome to another seminar of mathematics and high energy physics at Physics Latam. Today we are happy to start this mini course on supersymmetry with Professor Silvia Penati. She obtained a PhD in '88 at the University of Milan, and after she continued with a postdoc at Brandeis University. Currently, she is professor at the Milan Bicocca University in Italy. Her interests are mainly supersymmetry, string theory, and theoretical of high energy physics. We are very happy to have her with us today for this series of lectures. If you have any question at any moment, please raise your hand, and I hope you enjoyed this course. Now I leave you with Penati. Please go ahead.
Oh, it's nice to be here to give this set of lectures in supersymmetry. Well, first of all, I would like to thank Daniel for organizing this beautiful set of conferences and lectures. This is a very great idea. Thank you all for being present today. So what I'm going to do is a very basic introduction to supersymmetry. So we can call this course Introduction to Supersymmetry. Okay. Okay, it will be a very, as I said, very basic course. So what I will assume is that you don't know anything about supersymmetry. You have never been exposed to supersymmetry, at least not in a very systematic way. So if there is any of you who instead has already a few lectures in supersymmetry or read something about it, it will be a nice, at least the first part of my lectures will be a nice reminder, though it might be a little bit boring, but anyhow, I will assume that you don't know anything. Okay, so let me first of all mention sort of plan of my talks, of my lectures. Remember, these are 7 lectures, 2 hours each. Okay, so I will first of all, since we have no enough time to, to go through all possible formulation of supersymmetry, all possible dimensions, I will primarily focus on 4-dimensional theories and primarily on n equal to 1 SUSY theories. You will see that I will mention something about extended supersymmetry, but not much. I mean, most of the details will concern n equal to 1 supersymmetric theories in 4 dimensions. So the plan of my talk is today is to start with some motivation of SUSY. Then we will move to n equal to 1 SUSY algebra, SUSY transformations, and algebra. We will then analyze the representations of SUSY algebra. And this is very important because, as you will see, we can classify particles and therefore local fields describing these particles in terms of irreducible representations of the supersymmetric algebra. Then we, as I said, I will give a very brief introduction, but not much. Introduction to extended supersymmetry, which means, theories with a larger number of supersymmetric supercharges. Then I will give you a geometric construction of n equal to 1 superspace and how to formulate a supersymmetric theory in superspace. This always in 4 dimensions, of course. In this setup, we will study the simplest example of a non-trivial four-dimensional supersymmetric theory, which is the Vezzolino model. As the simplest example. Okay. Then hopefully we will manage to reach the point where we can introduce n equal to 1 supersymmetric gauge theories. And in particular for this set of theories, I hope to be able to say something about non-renormalization. So let's say we will study a little bit of quantization for these theories. At the quantum level, we will discuss some non-renormalization theorems. And in particular, something that probably you know already or you heard about it already, which is the finiteness of n equal to 4 super-Yamins theory. Super-Yamins theory. Okay, then there are a lot of more advanced topics, even probably more recent topics, advances, but we will not have time to go through them. So I can give you, in case you are interested, I can give you some references where you can find some advanced topic. Okay, a few words about references. Okay, there are many references, good references on supersymmetry. I just mentioned what I'm going to use, more or less. Okay, there are a lot of papers. First, let's start with books. There are a lot of nice books. The main books that I will refer to are first of all, the book by John Turning, which is called Modern Supersymmetry. Then you know that there is the quantum field theory book by Weinberg. These are 3 books, and the third one is devoted to supersymmetry. So Weinberg, Quantum Field Theory, the 3rd volume. Another book, which is probably not the best one for a first reading and a first studying, maybe this is already something more advanced, is the book by Jim Gates, Mark Grisaru, Martin Rocek, and Warren Siegel, which has a long title. It is a super space and 1001 lessons in supersymmetry. Okay, these are more or less the books that you might want to look at. Then there are a lot of very nice reviews that you can find in Inspire, easily find in Inspire. The ones that I usually suggest, review papers, are the famous and the historically famous review by Sonius. Okay, this is a physics report 128, 1985. Okay, this is very old review, therefore cannot be useful if you look for some more recent advances in supersymmetry, but it is definitely a great review if you want to understand the physical reasons why people back in the 80s, in the 70s, studied a lot supersymmetry. Okay, some more recent review is instead a review by Matteo Bertolini. You can find it in Inspire. There is a nice review by Bilal. This I know the number. This is TH 0101005. Okay, I think, and then there are many others. You can just Google supersymmetry and you find a lot of interesting references. Okay, more or less, however, these are the ones that I will refer to. Okay, now there are some prerequisites that you need to know before we start. Of course, I will give for granted that you know quantum field theory. I will give for granted that you know gauge theories in particular, that you know something about Lie groups and the algebras. Okay, so let me. For sure, you have to know quantum field theory. You have to know, in particular, gauge theories. As I said, Lie groups and Lie algebras, and in particular representations. Let's say technical prerequisite is that you should know something about, let's say, spinor conventions and operations with spinors. Usually this is not something which is very familiar to most people, so I will spend it sometimes now to review spinor conventions and the way we deal with spinors, because this is the basis of what people do in supersymmetry, of course, since supersymmetry implies dealing with the supercharges. As we will see, supercharges are spinors, therefore we need to learn how to do calculations with spinors. And of course, I will go through the basic notions about spinors, not because you don't know it. Of course, I assume that you know Lorentz representations, spinorial representations, but primarily to fix my conventions and my notations. I must say that probably one of the most difficult things in studying supersymmetry on different references is that every reference uses a completely different conventions compared to the others, because these are really, you know, set of arbitrary conventions that you can decide to use. The only important thing is that when you fix your set of conventions and your set of notations, you have to stick to this set of conventions, never change it along the calculations, of course. So I will tell you which are my conventions for spinors and how we will do operations with spinors. Okay, so this is what I'm going to review for you. So first of all, as I said, we will work in 4 dimensions, and in particular, we will work in 4-dimensional Minkowski space-time, where we will choose the metric as mostly minus. So for me, the metric is 1, the time component, and -1, -1, -1 for the space components. Okay. we know that we can classify spinor in general. We can classify representation of the Lorentz group. Again, among the classifications of the representation of the Lorentz group, we find in particular spinorial representations of Lorentz group. The lowest one being and you know that, representations of the Lorentz groups are labeled by two numbers, two half-integer numbers or integer numbers, which refer to SU2 representations. So the lowest dimensional spinorial representations are what we call the 1/2 0 and the one that we call 0 1/2. This is nothing but the left-handed Weil spinor that we indicate in this way as psi alpha 0 with alpha equal to 1 and 2. Okay, and 0 1/2 is what we call the right-handed Weil spinor. Let me call it psi r, which is instead 0 chi bar, I use chi bar alpha dot with alpha dot equal to 1 dot, 2 dot. Okay, these are, of course, in 4-dimensional spinors have 4 components. The Weil spinors, as you know, have only 2 components, difference for 0, and each component is a complex component. Okay, so while the left and right Weil spinors are made up by 2 complex components. For the time being, you should pay attention to the position of the spinorial index. This is just convention, but as long as I don't know how to move the spinorial indices up and down, you have to stick to my conventions, which means that left indices are down and right indices are up. Okay. Starting from Weil spinors, of course, you can construct a Dirac spinor. Just putting together 2 Weils. Let me call it psi d, and this will be an object which has 4 non-vanishing components. Again, alpha is equal to 1 and 2. And alpha dot is equal to 1 dot, 2 dot. Okay. And these are 4 complex components. Okay, now we know that we act on spinors with gamma matrices. So I need to introduce a set of 4 gamma matrices. Gamma mu equal to 0, 1, 2, and 3, that as usual have to satisfy the Clifford algebra. Okay. How do we define in our conventions? As you know, you can find the different definitions of gammas, all satisfying the correct Clifford algebra. How do we define our gamma matrices? Okay, we will choose the following definition, which is basically choosing the basis, what people call the Weil adaptive basis. So in order to define our gamma matrices, let's introduce 2 by 2 matrices defined this way. These are 4 2 by 2 matrices with indices alpha, alpha dot, which by definitions for mu equal to 0 is the identity, whereas for mu equal to 1, 2, and 3 are nothing but the Pauli matrices. okay? And I will label the entries of the matrix with this alpha dot indices. It means that, you know, for me, any sigma is a matrix of the four, let's say sigma 1, 1 dot, sigma 1, 2 dot, sigma 2, 1 dot, and sigma 2, 2 dot. Okay. This is not the end of the story. Let me define also a sigma bar mu. Now I will put indices up and in the opposite order. So here I have alpha dot alpha. And by definition, these are still the identity for mu equal to 0. Whereas for mu equal to 1, 2, and 3, I will choose minus the Pauli matrices. This with indices alpha dot in this alpha dot alpha. Okay, starting with this 2 by 2 matrices, I will build up. You know that in 4 dimensions, gamma matrices are 4 by 4 matrices. I will build up my gamma mu in the following way. These are block 2 by 2 block matrices, where I have 0, a 2 by 2 matrix 0 here on the diagonals, whereas here I will have sigma mu, and here I will have sigma bar mu. This is the definition of gamma mu. Okay, let's see how this gamma acts on a Dirac spinor. So what is the meaning for us? Writing gamma mu acting on psi. Okay, this will be, of course, this matrix 0, sigma mu, sigma bar mu 0. But then I have to put all the indices. Let me call this psi and chi bar. Now I will indicate for you explicitly the spinorial indices. This is alpha, remember, and this is alpha dot up. How do I label the indices in the components of gamma? This will be alpha, no, this will be beta, alpha. This will be still alpha up, but beta becomes beta dot up. This will be beta down and alpha dot down, and this will be beta dot alpha dot. Okay, this is to show you that if I perform the usual trivial product of a matrix times a vector, what you get as a first entry is exactly sigma mu beta alpha dot chi bar alpha dot, whereas the second entry is given by sigma bar mu beta dot alpha psi alpha. So what I want to show you, what I wanted to show you is that eventually I do find, of course, my 2 by 2 matrix is a sigma bar acting on the 2 by components of the Dirac spinor, but in a very specific way when, as usual, we use the convention that repeated indices means sum, but the repeated index, let's say left, goes from up to down, whereas the repeated index right, alpha dot, goes from down to up. This is convention, of course, but it's something that we have to define. We have to declare which is our convention. So more generally, the product of two spinors for us is defined as, so if I have two spinors, let me call them zeta and eta, and I do not write any index, by definition for me, this is zeta alpha, eta alpha, with this up-down rule. Okay, and similarly, if I have z bar, eta bar, similarly, but it's not the same, this for me will be zeta bar alpha dot, eta bar alpha dot, which means the opposite direction. Okay, you can find, I think using this kind of conventions, more, yeah, close to what probably you can find in turning in the book, but you can find many other review and papers and books where the convention is different, opposite, whatever. Okay, so this is my convention. Very good. We know that Pauli matrices satisfy the algebraic relation that if you have sigma I times sigma j, this is equal to delta ij plus I epsilon ijk. Epsilon is the usual antisymmetric tensor in 3 dimensions. Sigma k. Okay, using this property for the gamma matrices and recalling that our, let me go up a little bit, recalling that our sigma mu and sigma bar mu are defined in terms of Pauli matrices, okay, for which I know that we have this nice algebraic identity. You can, so starting from this, exploiting this identity, you can prove, and I invite you to prove it, you can prove the following more general identities for our sigma mu and sigma bar mu. You will find that if you multiply sigma mu times sigma bar mu, okay, and multiply for me means that I'm really doing the usual matrix product where I'm summing up on the alpha dot index, and I add the same product with the mu exchange with mu. You can prove, do it, that this is equal to 2 eta mu nu times delta alpha beta. Okay, so this is the first identity. And related to this identity, we also have, for instance, that sigma mu alpha dot sigma bar mu beta dot beta. Look, at this time I'm summing up the mu index, the tensorial index. I'm not summing up any spinorial index. So you have alpha dot beta dot free. Okay, this is equal to 2 times delta alpha beta delta alpha dot beta dot. And finally, as a consequence of this identity, you can also write that sigma mu alpha dot sigma bar mu. Now I want to sum also on the spinorial index. Therefore, here I have alpha dot. This is equal to 4 delta alpha beta. Okay. If you are not familiar with this kind of basis yet, you have to learn a little bit, and you can practice trying to check these easy identities. Okay. Why I'm mentioning these identities? Because now if you use these identities and you remember that we express our gamma matrices, gamma mu, in terms of sigma sigma bar, from these identities, it follows that you can prove that if you compute gamma mu, the anti-commutator gamma mu, with our definition of gamma mu, you will correctly find twice beta mu. So the choice of our gamma mu is definitely consistent. This means that you have the identity here, of course, as a matrix. Okay. Okay, now let's go on because so far so good, but as I told you, let me go up a little bit to remind you. As I told you, I made a particular choice for the position of the left index here, which means down, a particular choice of the right index alpha dot, which means up. I would have done the opposite choice, but this is my choice. And as a consequence of this choice, I had to choose a particular position for the matrix indices, okay? And so far, this is what I have to use. I cannot move these indices up and down, but I can now introduce an object which will help me in defining also a way to raise and lower spinorial indices. And in fact, we introduce the SU2 invariant tensor that we call epsilon alpha beta. I would say tensors that we call epsilon alpha beta and epsilon alpha dot beta dot. Okay. Defined this way, even here, it's just convention. So I have to tell you which is my convention for epsilon alpha beta. So epsilon alpha beta for me is 0, -1, 1, 0, which means that epsilon 1, 2 is equal to -1. Just question to remember this definition. Then, of course, epsilon to 1 is the opposite. I define the same way epsilon alpha dot beta dot, which is 0, -1, 1, 0, which means in particular that epsilon 1 dot 2 dot is equal to -1. Okay. And I will introduce also the invariant with upper indices. We also define epsilon alpha beta and epsilon alpha dot beta dot, such that if you compute epsilon alpha gamma, epsilon gamma beta, so basically you are computing epsilon square, you get the identity, which means delta alpha beta. Okay. And similarly, if you compute epsilon alpha dot beta dot epsilon, epsilon alpha dot gamma dot epsilon dot beta dot, you get delta beta dot alpha dot. Okay, it's just a question to look at the previous definition to realize that epsilon alpha beta up is exactly the opposite of the epsilon alpha beta down. Therefore, epsilon 1, 2 up is equal to 1. And the same for the dot. This is 0, 1, -1, 0, which means that epsilon 1 dot 2 dot is equal to 1. Okay. Okay, it's easy to remember. You have just to remember how you fix the first component. For instance, epsilon 1, 2 down is -1, then epsilon 1, 2 up is the opposite. No problem. Okay, why I'm happy with these objects? Because now I can contract this epsilon matrices with my spinors to define lower and upper spinorial indices in this way. So remember that for left spinors, we introduced psi alpha with alpha down, but now I can associate to psi alpha down another representation of the Lorentz group, which is however equivalent to this one, to psi alpha down, but it will have the upper index by definition given by epsilon alpha beta psi beta, where as usual, if I have the repeated indices, it means that I'm summing over this index. Okay, and similarly, remember that for the right spinors, we introduced the notation chi bar alpha dot with alpha dot up, but now I can define a corresponding chi bar alpha dot down, still given by epsilon alpha dot beta dot psi bar beta dot. Okay, this is kind of nice because, for instance, you have this nice correspondence. Suppose you are dealing with the first component, alpha equal to 1, psi 1. This psi 1 has a corresponding psi 1 up, which is equal to what? Epsilon 1, 2, psi 2. Do you agree? Because epsilon 1, 2 is the only non-vanishing component of epsilon when I fix the first entry to be 1. Okay, let me go slower. So in principle, by definition, this is epsilon 1 beta psi beta, okay? But the only, if I look at epsilon, this epsilon, the only component which has, the only non-vanishing component which has as a first entry 1 is epsilon 1, 2, which is 1. Okay, therefore this is, therefore this is equal to epsilon 1, 2, psi 2, which is psi 2. So psi 1 up is equal to psi 2 down. And you can go on and play with the indices and check that there are all these kind of identities. Okay, therefore, we have a very important general identity, which is the following. Let's go back to the contraction of two spinorial indices. So let's consider the product of two spinors. As we said, for us, the definition is psi alpha, psi alpha. This is the way we contract the indices. But this is what? This is, by definition, epsilon alpha beta chi beta times psi alpha, okay? But this is also equal to, let me pull out psi beta times, let me invert the indices in epsilon. So I get a minus because the epsilon is anti-symmetric. But by definition, epsilon beta alpha psi alpha is psi beta up. So this is equal to minus zeta beta psi beta. Okay. So the general identity you have to keep in mind, this is very important, is that every time, I mean, at this point, you can move the spinorial indices up and down, but every time you move a pair of spinorial indices, of contracted spinorial indices, you get a minus sign. This is general in spinorial, you know, it's the typical thing that happens in spinorial algebra, which is the kind of different from what you have in tensorial algebra. No? When you contract a mu index, gamma mu, or you contract gamma mu down, gamma mu up, you don't get any sign. For the spinorial indices, you do get a sign, okay? And of course, if you redo the same reasoning for the bar, for the right spinors, similarly, you will get that Z bar alpha dot psi bar alpha dot, which is the way we define the product, will be minus Z bar psi bar alpha dot psi bar alpha dot down. Okay, that's why we have to be careful when we fix the conventions on the contraction of spinorial indices. Yeah, another way to state the same identities is the following. If you have, because it follows that if you have Z psi, this will be equal to psi Z. Okay, why? Let me do for you the calculation. Z psi by definition is Z alpha psi alpha, okay? However, this is equal to, remember that the spinorial components are anti-commuting objects, so this will be minus psi alpha, Z alpha minus because I'm anti-commuting the two spinors, but this is when I move the indices up and down, I obtain another sign. So this is psi alpha. So I'm back to plus, and by definition, this is psi chi. Okay. The last boring convention, then we can do something more, it's still convention, but something more, let's say, physically relevant. The last boring convention is the following. So now that I know how to move spinorial indices up and down, remember that my sigma mu and sigma mar mu matrices, they carry spinorial indices, okay? So how do I define the way to move up and down spinorial indices on the sigmas? On the sigma matrices, I will define the following. So remember that sigma mu comes by definition with the lower indices. But at this point, I can certainly define some new, let's say new matrices with upper indices that by definition are given by epsilon alpha beta, epsilon alpha dot beta dot, sigma mu beta beta dot. So basically for each single spinorial index, I use the same definition for raising the index, okay? But the nice thing, and this is something that you should check that if you define sigma mu with upper indices this way, this is nothing but sigma bar mu, alpha dot alpha. Okay. And similarly, if you start with sigma bar mu, remember this has upper indices, you can define a sigma bar mu with the lower indices acting with epsilon. Alpha dot beta dot, sigma bar mu beta dot beta, and you will find that sigma bar mu with the lower indices is nothing but sigma mu. These are kind of important identities. Okay, as I said, I'm listing a number of identities, and I'm not going to prove all of them. So in order to practice, you should try to prove these identities. Okay. Yeah, I need still one single information. How do we define Weil projectors? Remember that when we have a set of gamma matrices, we can define the famous gamma 5, which is by definition I, gamma 0, gamma 1, gamma 2, gamma 3, with the particular set of gammas that we have introduced. You can prove, it's easy, just do the multiplication, that this is equal to minus the identity. This is a 2 by 2 block matrix, minus the identity 0, 0. Okay, therefore, well, it's easy. The biprojectors are the following. If I define a projector given by 1 minus gamma 5 over 2, this is the identity 0, 0, 0, and it, of course, it will project a Dirac spinor on its left-handed components. So it will be psi alpha 0. And similarly, if I define a right projector as 1 plus gamma 5 over 2, this will be 0, 0, 0, 1. And therefore, when you apply the right projector to a Dirac spinor, you will select the right Weil spinor. Okay, so what I was mentioning about something more physical concerns, for instance, the conjugation rules for spinors. For spinors. Okay, we can define, as you know, two kinds of conjugation rule. The first conjugation rule is what we call the Dirac conjugation rule, or if you want, the Dirac conjugate of a spinor. How? This is just definition. By definition, the if psi is given, so given, let me do it this way, given a Dirac spinor psi, we define the Dirac conjugate, and we call it psi bar, to be psi dagger gamma 0. This is something that you know. Okay, in our conventions, let's see what happens. In our conventions, we have that gamma 0 is 0, the identity 0, remember. Therefore, and moreover, psi, the original psi is psi alpha chi bar alpha dot. So what happens when I compute psi bar? What I find is, okay, the dagger of psi, dagger, remember, means complex conjugate and dagger. So dagger means that I get a line vector. And then in the components will be, of course, psi alpha star, chi bar alpha dot star, times gamma 0. Okay. And this is, if you perform the product, of course, this is chi bar alpha dot star, psi alpha star. Okay. Now, the question is how we do define the complex conjugate of the vial components. We define, and this is again convention. You can find different conventions in different books, in different reviews. The important thing is that what you build up is something consistent. In our case, we define psi alpha star, let me call it, minus psi bar alpha dot. And chi bar alpha dot star to be minus chi alpha. And consistently with these definitions, we will have that psi alpha up star is equal to minus psi bar alpha dot, and chi bar alpha dot down star is minus chi alpha down. Okay. Remember that up and down means that we are multiplying by epsilon alpha beta or epsilon alpha dot beta dot. These are real tensors, so they do not change the rules in the conjugation of the vial components. Okay, this is our definition. Therefore, if we go back, we reach the conclusion that according to this definition, our psi bar here will be minus chi alpha minus psi bar alpha dot. This is the definition of the Dirac complex conjugate. Okay, but we have another conjugation rule, which is the charge conjugation. Okay, charge conjugation, remember, requires introducing the charge conjugation matrix that usually people call C, which by definition is minus I gamma 0 gamma 2. And using this conjugation matrix, we define another conjugate, let's say another conjugate of the spinor. Let me call it psi C, which by definition is the application of the charge conjugation matrix to psi bar, the Dirac conjugate, transpose. This is a standard definition that you find in any quantum field theory book. But now we have to see what happens in our conventions. Okay. First of all, this is nothing but minus I gamma 0 gamma 2. Well, let me just, sorry. I can rewrite this as I gamma 2 gamma 0, which is C. And then I have to take the transpose of the psi bar. But psi bar, remember, it's psi dagger gamma 0 transpose. Okay, so this is I gamma 2 gamma 0 gamma 0. Psi dagger transpose is nothing but psi star. So it is I gamma 2 psi star. And if you do it explicitly, do it. We know now what is gamma 2 for us. We know what is the definition of psi star because we gave here all the rules to compute the complex conjugate. You will find that this is equal to chi alpha psi bar alpha dot if we started as usual with psi, which is psi alpha chi bar alpha dot. Okay. The main thing that we need to stress is that once you have defined the charge conjugate of a spinor, of a Dirac spinor, we can ask the spinor to be Majorana, remember, okay? And this is very important because you will see that all our objects will be Majorana spinors. What is a Majorana spinor? By definition, a Majorana spinor is a spinor which satisfies the condition that psi is identically equal to psi conjugate. Okay, in our conventions, it means that psi alpha chi bar alpha dot, which is the original spinor, has to be equal to chi alpha psi bar alpha dot. Okay, so what I read from here is that, for instance, chi bar alpha dot is nothing but psi bar alpha dot, the complex conjugate up to a sign, the complex conjugate of psi alpha. Therefore, a Majorana, let me call it psi Majorana, has the following form: psi alpha, psi bar alpha dot, where, as I said, psi bar alpha dot is the complex conjugate of psi alpha. Okay, and in fact, what happens is, of course, that this constraint that you now require on Majorana spinors halves the number of degrees of freedom in a spinor. So starting from a Dirac spinor, which depends on 4 complex entries, 4 components, you end up with a Majorana spinor, which contains only 2 complex components, because psi bar is the complex conjugate. Okay. Okay, remember this, in particular, keep in mind this, how is a Majorana spinor reads in our conventions. Okay. This is it for spinors. Sorry, I have to be still a little bit boring, but it's important that we fix all the conventions. If you don't mind, I will go through this last set of convention, then we can stop for the break, okay? Because that will be a good point where we can stop. So the last thing that I have to recall, I don't know if it is just recalling or you have to learn for the first time, is how to use the double spinor notation for tensorial algebra. Okay. Double spinor notation for tensorial algebra. What do I mean with that? Let's take the simplest situation, which is, for instance, I'm dealing with a covariant vector. So let's take a covariant vector. Let me call it v mu. You know that mu can have values 0, 1, 2, 3. Okay, so a vector in 4 dimensions has correctly 4 components. I want to introduce a different set of components for my vector. Basically, I'm going to change the basis because it will turn out that it is more convenient to use this other set of components. So rather than using components v mu and index mu to indicate the components, I want to move to another set of components that we will call v alpha alpha dot. How are they defined? We define them in the following way. V alpha alpha dot, by definition, is, forget about this prefactor, this is just convention. But the important thing is that this is given by sigma mu alpha alpha dot v mu, where mu, as usual, is sum because it is contracted. Okay, it means that if we start with a set of 4 components, the usual ones, now we will deal with another set of components that we will indicate this way, which are of course still 4. I cannot change the number of components, but they are given by what? If you look at this definition, you immediately realize that basically the new alpha alpha dot components are nothing but a linear combination of the mu components. Precisely, if you remember how we define our sigma mu, remember that sigma 0 is the identity. Sigma 1, let me put in this way. Sigma 0 is the identity. So we only have diagonal components. Sigma 3 is the third Pauli matrix, which has only diagonal components, whereas sigma 1 and sigma 2 have off diagonal components. Okay. Therefore, if you perform this multiplication, this one, where you sum up mu on 0, 1, blah, 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 you will find what? You will find the following explicit relation. So if you compute V1, 1 dot, you have to look for the matrices here that have 1, 1 dot components. And these are only the identity and sigma 3. Okay. So this is, of course, 1 over square root of 2, V0 plus V3. If you look at the 2 component, 2 dot component, same story, but with a sign. So you will get V0 minus V3 because sigma 3 has a minus sign in the second component. Whereas if you look at the components 1, 2 dot and 2, 1 dot of diagonal components come only from sigma 1 and sigma 2. Okay. And if you consider, you take into account how sigma 1 and sigma 2 are defined, you will find that V1 2 dot is 1 over square root of 2, V1 minus IV2, and V2 1 dot is V1 plus IV2. Okay, you can check yourself that this is the way we map the original components into the new ones. Okay, the mapping is invertible. So if let me go back to the definition that we have here for, do you see my pointer? Okay, fantastic. Okay, here we have the definition of the new components in terms of the old ones using the previous identities that I wrote for sigma and sigma bar. You can now invert this relation and find the old components in terms of the new one. In fact, inverting, you can check that V mu is equal to 1 over square root of 2 sigma bar mu alpha dot alpha d alpha alpha dot. So you can go from the old to the new ones or vice versa using these two identities. Okay. We have in particular in a field theory, in particular, we have important vectors, which are the coordinates. So the same thing we do for the coordinates. And in fact, starting from a set of 4 coordinates, satisfying all the conditions that you want them to satisfy, you can define the new set of coordinates, which, well, here already, I already said that these numbers are just conventions. The most important thing is that this is how you contract the old coordinates x mu with the sigma bar this time in order to generate the new coordinates. Or you can invert this relation and write the old in terms of the new ones. X alpha phi dot. Okay, in the same way, if we define the derivative with respect to the old coordinates, the derivative will have a corresponding alpha phi dot number of components, which by definition is sigma mu alpha phi dot d mu. And of course I can invert, therefore d mu is 1/2 sigma bar mu alpha dot alpha d alpha phi dot. But the main point, you have to check all these identities. Now I'm going a little bit fast, otherwise we will stop forever on conventions. Okay, you can easily check everything. The main identity that I want to stress is that if you now apply d alpha alpha dot to x beta beta dot, this is equal to delta alpha beta delta alpha dot beta dot. Check it. But this is the analog of what you would write in the old coordinates when you write d mu x nu, which is delta mu nu, right? This is the analog in the new set of coordinates. In particular, what happens now if I compute d alpha alpha dot and I contract this with d alpha alpha dot? Of course, up or down indices now can be moved using the epsilon tensor. Okay, you simply insert the definitions that I gave you here for d alpha alpha dot up and down. So you will find that this is sigma bar mu alpha dot alpha d mu times sigma nu alpha alpha dot d nu. For this, we have already a nice identity that I mentioned at the beginning. Not all of this, but for this times this, we have already a nice identity. Therefore, if you use that identity, this will be equal to 2 eta mu nu d mu d nu, which is nothing but 2 d mu, which is what we call 2 box, the ordinary Lorentzian box operator. Okay, so another important identity that we will probably use is that when we write box in our set of conventions, it means 1/2 d alpha alpha dot d alpha alpha dot. Okay, very last identity that it's very useful when you do calculations is what people call the Firth identity or identities. We have 2 of them. Okay, suppose that you have a spinor, let me call it A alpha, and another spinor B beta. If I multiply them, I'm not summing over alpha beta, just ordinary multiplication, and I subtract A beta B alpha. So I am anti-symmetrizing in alpha and beta. This is equal to epsilon alpha beta A gamma B gamma, this time contracted. And you have the same story for dot, but you have to be careful with the order of indices. This is equal to epsilon beta dot alpha dot, this time A bar gamma dot B bar gamma dot. If I want to keep the convention that up down for left and down up for right indices. Okay. We have done with conventions. Sorry, it's always a very boring part. Sorry, but it has to be the first part because otherwise you will be not able to follow what I'm going to tell you later. Just to put you in a comfortable situation, at least we mentioned how we will deal with spinors and how we will use double spinor convention for tensorial algebra. Now I think we can have 5 minutes, that's 12. Okay, so this concludes my part about prerequisites. Now we enter the subject, okay? So as I promised, I will give you first sort of historical motivation why people introduced supersymmetry. And in order to do that, I have to say something about symmetries in general. Okay, what I mean with symmetries, of course, we know that quantum field theory is based on symmetry principles. And in particular, I will briefly review the two main principles, which are the following. Symmetries are used to classify particles. To classify particles. And symmetries, in particular, local symmetries, so gauge invariance. Define local interactions. Okay, let me very briefly go through these 2 points. This is really sort of recalling, you know, these things very well. So let me first of all consider point 1. Remember that we have everything relies on the Noether theorem, which tells me that to each invariance of the action, there is a conserved current, a corresponding conserved current, variance of the action. We have correspondingly a local conserved current. Let me call it generically J mu. So we will have this nice relation, which allows us to define, we can define the corresponding charge. Let me call it Q, which by definition is the space integral of J0, which will be a function of x0 and x bar, such that it's easy to see that Q is conserved. Okay, this is very important because if Q is conserved, we can use the corresponding, suppose that Q is this point generator of this, well, it's conserved. Okay, let me say, and it generates symmetry transformations. Therefore, in particular, if Q is conserved, the corresponding eigenvalues are conserved, and the corresponding eigenvalues can be used indeed as well-defined quantum numbers to classify particles. Are conserved, therefore they are good quantum numbers to classify particles. Okay. We know how things in particular work when we consider Poincare invariance. You know that by definition, any quantum field theory is Poincare invariant. So let's consider in particular for the time Poincare invariance. We know that the corresponding generators, or if you wish, the generators for whose eigenvalues can be used to classify the particles are the momentum. And in fact, translational invariance corresponds to conserved momentum, and mu nu, which are the Lorentz generators of the angular momentum. Let me put it this way: conserved angular momentum. Okay. Therefore, we know that d mu, p mu is equal to 0. Rather than considering mu nu, it's better introducing the Pauli-Lubansky vector called W mu, which by definition is 1/2 epsilon mu nu rho sigma p nu m rho sigma. This is Pauli-Lubansky tensor or vector. Okay, why it is more convenient to use W? Because now it's easy to see that if we construct P square and W square, these are two Casimir operators for the Poincare algebra. Poincare, remember, is called ISO 1-3. So let me be more coincide for ISO 1-3. What is the meaning of being Casimir operators? It means that these two operators, these two generators, commute with all the generators of the algebra. Okay, therefore, their corresponding eigenvalues can be used to classify particles. And in fact, particles are classified basically in terms of the irreducible representations of these operators. What happens is that we have to split basically the situation where, well, sorry, let me first of all say that P square has eigenvalues that we call m square. Therefore, we have to split the case where m square is different from 0. In this case, you can go to the rest frame of the particle. Sorry, m square, by the way, is what we identify with the square of the mass of the particle. And in this case, you can prove that W square is proportional to m square times the angular momentum square. Therefore, the corresponding eigenvalues are of the form m square s times s plus 1, and we have a second quantum number, which is s, to complete the classification. So S is what we call the particle spin. Okay. So in the massive case, we have two quantum numbers, which are the mass and the spin, to classify all the particles. In the massless case, in this case, what you can do is to easily prove that W is proportional to the momentum P, with lambda, which can be plus or minus a number, which is called helicity. Okay, so in this case, we can have only two possible for a fixed particle. We can find only two possible states, plus or minus S. Okay, but this is not the end of the story, as you know, because in addition to Poincare invariance, which is always present in quantum field theory, we can even have theories which are invariant under some internal symmetry. Okay, what is the meaning of internal symmetry? Means that we can have additional invariances under the action of the, that we call TA generators of the group that in general satisfy some algebra relation of this form, where these are the structure constant of the corresponding algebra. Okay, we have millions of possible physical examples. Remember that, for instance, we can have internal SU2 invariance, which is the isospin invariance. We can have flavor SU3, and we can have an arbitrary number of U1s. Number of U1 symmetries. Okay. This is all what we know concerning how to classify particles, because at this point, of course, if I have additional symmetries, I can always use you know, the eigenvalues of the Cartan subalgebra of these internal symmetries to pick up other quantum numbers which can be used to better specify kind of particles. Okay, so we can use the conserved eigenvalues. Sorry. Of Cartan subalgebra to classify. No, and let me put it this way, as further quantum numbers to classify particles. Okay. Then we have, okay, for point one, we can stop here. You know very well of this part. So this was point one, which means how do we exploit symmetries to classify particles. Point two is what we call a gauge invariance. So let me just review briefly. Sorry. Point two. So local invariance implies local interactions. In fact, suppose that we have invariance of my theory, of my action under an internal group of symmetries generated by, as I already wrote, some generators which satisfy typically a non-trivial algebra. Okay, it means that if my theory is expressed in terms of local fields, let me call it generically phi, phi of x transforms into a phi prime of x that will be given by e to the I alpha a t a phi, where t is given in a given representation depending on what phi is. Okay, but as long as we discuss the classification of particles, of course, this is an internal rigid symmetry, which means that alpha, these alphas are constants. Okay, but now what we can do is to we can promote alpha a to be a function, a local function of space-time. This, of course, breaks the symmetry of the action unless, so this breaks the symmetry unless we introduce a new vector field, let me call it a mu, to covariantize the action, which means that basically if the action contains derivatives respect to space-time coordinates, this has to be replaced by a covariant derivative, which is the old derivative minus some constant g times a mu a t a. Okay, and these are new vector fields, which are nothing but the mediators of fundamental forces. Okay, and in fact, we know that electromagnetic force corresponds to U1. We have standard model for the electroweak, which corresponds to SU2 cross U1. Then we have a QCD, which corresponds to SU3, so on and so forth. Okay. Good. Given this picture that you know, let me just mention a couple of things. In particular, let's go back to the classification of particles. So let's consider a theory, a quantum field theory, which by definition is invariant under Poincaré. Plus, let's assume that it is invariant also under some internal symmetry generated by T. Okay. The observations that I want to make are the following. So let me first of all write something. So now, suppose we have a quantum field theory with internal rigid symmetry generated by TA. Okay, so the complete set of generators acting on the fields of my theory and which leave the action invariant will be what? Will be the generators of the Lorentz and translations, so Poincaré, and this TA. We know that we can write the action of these generators on fields as suppose that we consider infinitesimal transformations. Okay, we will have that in general, the variation of phi respect to the action, due to the action of the momentum, so translations, can be written this way, P mu acting on phi, these are translations. Delta phi due to a rotation or boost or Lorentz boost can be written this way. Rotations plus boost. Okay, and the variation of my field due to the action of the internal symmetry will be something like this. Okay, if we keep considering infinitesimal transformations. Okay, what typically happens is that, you know, first of all the generators of my set of invariances, my set of symmetries are, as we say, bosonic generators, in the sense that they satisfy commutation rules. Okay, they all satisfy commutation rules. Therefore, the corresponding parameters that I will have here describing my variation are bosonic quantities. Okay, which means that varying, for instance, a bosonic field, I don't know, a scalar, I will end up with something which is still expressed in terms of bosonic fields. If I vary a fermionic field, a spinor, I will end up with, on the right-hand side, something which is still a spinor. Okay, so the first observation, let's say observation number 1, since the generators satisfy commutations rules, the parameters A mu epsilon mu nu alpha A are bosonic parameters, bosonic quantities. Okay, therefore, we can, let me put in this way, we can never perform a transformation of a bosonic field, which appears here on the left-hand side, in such a way that the right-hand side is expressed in terms of fermionic fields. Is that clear? If here, let me put in this way, if here, let me go somewhere, forget that this is a translation. This is a, you know, something that I don't know, but what I'm doing here is I take my scalar field, let's start with the scalar. I perform the transformation of the scalar. I ask myself, is it possible that on the right-hand side, I will get as, you know, transform field, something which is a linear combination of objects which contain also fermionic objects, spinorial objects? Is that possible? I would say no, because if here I have some spinor, I should compensate the nature of this spinor with some, multiplying it with some other spinor. Okay, but I do not have any spinor, any spinorial parameter to combine with a spinorial field in order to give me something which is still a scalar. Okay, so what we can conclude is that in the standard situation, we never obtain transformations between bosonic now let's put not between, let me put that mix, let's put in this way, that mix bosonic and fermionic fields. Is that clear? Therefore, this means that if my Lagrangian, this is the Lagrangian, is written in terms of bosonic and fermionic fields, is something like L for the bosonic fields plus L for the fermionic fields, I will never be able, for instance, let's take the simplest situation. Example, let's consider, for boson, we consider a scalar, so L bosonic could be simply the kinetic term of the scalar. Let me add also the mass term. And for the fermion, let's take the usual Dirac equation, the Dirac Lagrangian for fermions. Let me put also the mass. So let's do it psi bar IT slash. Okay. We will be never able to mix the two Lagrangians using transformation. It means that under the standard set of symmetries, L bosonic is invariant itself and L fermionic is invariant itself. They never talk to each other. Okay, so they are invariant separately. Okay. Okay, the second observation, observation number 2. Typically when, you know, the set of transformations, as I wrote here, are generated by Poincaré plus some generator of internal symmetries, which can be generators, I don't know, of SUN, SON groups, this kind of things that typically we use to classify particles with quantum numbers. What the parameters, this alpha A, this parameter is first of all independent because these are global symmetries, rigid symmetries. So this is independent of X. So it is not subject to translations. And it is also a Lorentz scalar. So P mu and mu nu never act, or if you wish, they act trivially on the internal parameters. Okay? Is that clear? Good. So let me write this. So typically, the alpha A parameters of the internal symmetry are not affected by the action of P mu and M mu nu. In other words, they are X independent and Lorentz scalars. Okay, if we rephrase this statement in a kind of different way, this is equivalent to say that you have a non-trivial algebra for P mu and M mu nu generators. They give a non-trivial algebra. You know the Poincaré algebra. I avoid rewriting again. You have a non-trivial algebra for TA. This is the one that I wrote earlier. TATB equal to IFABCTC. Okay, they give a non-trivial algebra unless you are considering U1. But what happens is that P mu and N mu nu, they commute with the generators of the internal algebra. Okay. Therefore, the situation that I'm describing, the group in the group of symmetries is Poincaré times the internal symmetry. I don't know how to call it G. Okay. Now, at a certain point, for many different reasons, people start asking whether it would be possible to formulate a more general theory, a more general field theory, which is invariant under a different set, a complete set of, probably more general set of generators in such a way that, you know, the generators of Poincaré do not longer commute with the generators of the internal symmetries. Okay, this is the question. You can imagine that, you know, if you want to build up some more general theory, this is certainly some generalization that you could have in mind. Okay, so the question at this point is, can we construct a more general group of symmetries for a quantum field theory such that P mu and N mu nu no longer commute with TA. Okay, this is a question. The answer is, let's say no, as long as we stick to this specific kind of situations. The answer was given by Coleman-Mandula. In fact, the answer goes under the name of Nogo theorem of Coleman-Mandula. So the answer is no, according to Coleman-Mandula Nogo theorem. Okay, so let me summarize for you the statement of the theorem, then I can give you references where you can look for a proof. The statement of the theorem is the following. Okay. Okay, suppose we consider a four-dimensional relativistic theory for a finite number of massive particles. Okay, with non-trivial interactions. It means that we have a non-trivial S matrix. Okay. Good. If we require the S matrix to be invariant under a general group of transformations that contains Poincaré. ISO 13 as a subgroup. Okay. The only way not to spoil the analyticity of the S matrix is to have this big group, I don't know how to call it, general group, let me give it a name. Big G tilde. The only way not to spoil the analytics of the S matrix is to have G tilde of the form G tilde equal to ISO 13, so it means Poincaré times an internal symmetry. Okay, so the situation that we have pictured earlier, going through what we typically do in quantum field theory, is the most general one, because the no-go theorem by Coleman-Mandula tells us that we cannot do nothing, we cannot do anything better than this. I mean, the only possibility is to have, as I said, that the general structure of the complete symmetry group is always Poincaré times. When I say times, it means that the generators of the internal symmetries always commute with the generators of Poincaré group. Okay, we cannot have anything more general. Otherwise, what do we mean that we spoil the analyticity of the S matrix? If we force the most general group to be something not of this form, we end up with a nice matrix where, for instance, two particle processes can occur only for discrete value of the energy of the momentum, which is something not physical. Okay, so this is the reason why this is the only output according to this theorem. So for the proof, there is a nice proof in the third volume of Weinberg, volume 3, quantum field theory. And there is also a beautiful, if you manage to find it, I found it once, but I was looking at it again. I was no longer able to find it. If you can find, there is a nice, I would say beautiful paper by Witten in Erich lectures. Back to 1981. if you Google and you find it, please let me know and send me a copy because it's really a great proof. Okay, so people at this point were not still thinking of the situation from a historical point of view. At this point, people were not happy enough. So in order to overcome this no-go theorem, the only possibility that they had was to try to relax some of the assumptions on which the theorem is based on. And one assumption, which I didn't even mention because it was given for granted, is that we are dealing with ordinary groups. I mean, Poincaré is, of course, fixed, the usual group of invariances. But when we talk about the internal symmetries, it was somehow given from granted that we were talking about groups, okay, which means a group generated by, as I said, bosonic generators, which satisfy set of bosonic, where is it? Here, a set of bosonic algebra relations, which means the algebra is given by commutators, okay? But from mathematics, we know that the spectrum of all possible groups is not complete if we consider only bosonic generators, because we also have supergroups, which contain both bosonic and fermionic generators, which satisfy sets of commutation and anti-commutation relations, respectively. Okay, so one possibility for overcoming the no-go theorem was to go to move to consider also supergroups, which means including the possibility that internal symmetries can be generated by generators which satisfy anti-commutation rules, therefore by what we call fermionic generators. Okay, and this is basically the birth of supersymmetry. Okay, so let me just write, and then probably we have to conclude for today. So one way to overcome the no-go theorem is to allow for internal symmetries generated by fermionic generators, which means consider super groups. Okay, as I said, the fermionic generators means that, you know, I don't know how to call them, let me call them FA, with these generators. They satisfy anti-commutation rules. Okay, this can still be some let me call F tilde A, B, C, T, C, but the important point is that this is anti-commutation rules. Okay, so this was the historical motivation. Now we are going to stop for today, but next time what we will do is not going immediately through the algebraic construction, because this would be probably too shocking for you. I will try to introduce supersymmetry and anti-commuting generators, basically from scratch. I mean, starting from a very hand-waving construction of the simplest theory that we can imagine satisfying this kind of symmetries. Okay. Okay, I think I will stop. So if you have questions.